ahead and get started. So this session is meant to be a sort of a discussion, or at least I'll show some slides that might motivate a discussion about some application, actually solution that we have at TI called CMEM, which is solving some problems for our SOCs for a lot of the use cases we have, and a discussion of what could possibly replace that solution that's more open source, something that's more mainline. And I'll talk about one of the things I've been looking at, which is the new C and Alic stuff that's been being developed out of Linaro UMM gene, and see if that's applicable, or if not, if there's other, discuss if there's other things that might be more applicable. CMEM is a continuous memory allocator that TI created. There's the link for the overview. It handles buffer allocation, buffer management, and it's designed to meet a lot of our multimedia use cases on our SOCs. I shouldn't just say it's just TI SOC. I got an email the other day from a guy who's porting CMEM to Intel Atom, and he wants to do something with getting a buffer and passing it to an open GL context for endoscopic application. So the CMEM code really isn't very hardware specific. It's quite generic, and begs the question, why don't we just upstream this? And if not, is there something else that could do something that handles what we need that's also generic? So we use it for OpenCL use cases, complete use cases, and like I said, multimedia embedded use cases. And it's open source, but it's not in the Linux mainline tree. Mainline, it lives in a separate repo and a Git repo, TI Git repo. And as I said, we'd like to explore meeting these use case requirements using other mechanisms. And upstreaming CMEM may be an option if it's something that we think makes sense. So some of the use cases that we have, some of the requirements that we have that CMEM meets is the ability to allocate contiguous physical memory, for example, CMA, to create buffers that are shared between on the SoC, the ARM, and co-processors like DSP or smaller processors, or between ARM and a hardware accelerator, or DMA. We need the ability to allocate huge buffers, which is a little problematic right now. Can be done, but there's some issues there. We want the ability to be able to allocate from pools of fixed size buffers or variable size buffers. So heaps or allocation from pools of fixed size memory. And that's important for a lot of embedded applications because you don't want to, after running for a long time, get memory fragmentation. So you want to be able to have different pools of different size buffers and have your applications allocate from those pools of fixed buffers continually. And user space must be able to source and sync or read and write the buffers. So when you think about dma-buf, the solutions, the use cases for dma-buf, there's a sharing of buffers that are created from one device and exported and given to another device. In some of our use cases, we may have user space actually wanting to generate or consume the data, and so it has to operate as a source or a sink of the pipeline. So in that case, user space is kind of like there's no device driver that's going to export the buffer like a graphics driver. It can come directly from some application that user space is running in user space. Another use case is, other than OpenCL compute and multimedia applications, we have user mode Ethernet driver, transport layer, and in that case, it really needs the capabilities of a user space device driver, UIO type capabilities. So the ability to, in this case, the driver needs to program DMA configuration registers. It needs to get a block of memory, carve it up, and then pass those bits or chunks of the big block to DMA, to the DMA registers, the descriptors, to be able to do DMA from user space. So you need to be able to get the physical addresses of memory and be able to pass that down and program the registers. So that needs to happen from user space. So I mentioned, actually, it was in a slide, I don't know if I mentioned it, but so some of the devices that we have is the Keystone 2 SoC. That's a multi-core DSP device that's used in a lot of computational servers. OMAP 3 and up type devices where we have ARM DSP cores and different kinds of accelerators. And one of our original DaVinci platforms. So this current solutions that we have for meeting those requirements, CMEM is living in this tree, in this Git tree. I mentioned it's a contiguous physical memory allocator, has a kernel module and a user space API. Used on several of those platforms I just mentioned, ARM plus accelerator type platforms. And the way it works is first you need to reserve some memory, and you can use CMA type memory or carve out. If you're using CMA, you could either use the global CMA pool or device specific CMA pools. If it's set up for the global pool, we just call DMA Alic coherent. If we need to set up separate pools, then we go into the platform's machine start reserve function and make a call to DMA declare contiguous and reserve some memory for CMEM for all the different use cases. So if it's a carve out, then that's through Linux boot parameters, like a mem equals size at address line to take away memory from Linux, so it's reserved for the CMEM device driver. Now, so again, the CMEM device driver, it is a device driver, but it's not really tied to the DSP yet. I mean, it's under the covers of the platform. Yeah, it's calling the DMA APIs, and under that, through callbacks, it's calling into the platform to do the right DMA operations and any IOMMU type operations that are needed for the platform. But the CMEM driver itself isn't. It's pretty generic. It's a pretty generic code. So once you've reserved these blocks of memory, you do memory allocation. CMEM does the memory allocation by implementing either a heap module, which calls Alic and free, do standard kind of memory allocation from this reserved heap, this reserved block, or given one of the, if you're doing pools of fixed buffers, it carves up the physical memory and keeps track of what buffers are being allocated within that physical memory. So it implements a memory allocator. There is some concept of buffer tracking, kind of ad hoc, per file descriptor, buffer ownership, and if a process goes away that's holding one of these buffers, then there's some cleanup that happens. Because right now, CMEM isn't handling DMA-buf. It's not supported right now. And then once you allocate the memory, you're allocating a physical buffer, you get a physical address. CMEM allows you to map that into user space. So that's using the remap PFM range function. And then setting the cache or non-cache bits for that memory. So you can allocate physical memory, you can map it into virtual space, you can specify whether it's cache or not cached. And that's basically what this does.
Can it allocate memory that's reserved for like security? Like, you know, I block this 100 megabyte chunk of memory for secure memory. So it cannot actually see the memory, but all it needs to allocate is like physical addresses in that space. Can it do that?
If you know where that memory is,
Yeah.
then you can specify, well, with the carve out, is it memory that Linux knows about, or is it carve out?
It doesn't matter. Let's just say pick one, right? Like, you know, carve out. Let's just say that, you know, starting at this address to this address. Can we just give that specification to CMEM saying that that's going to be secure memory, but I don't want to right now the allocator. I just want to use CMEM for it. Can it do that?
You can specify the area of carve out with DMA declared contiguous. I believe you can specify the address there.
Okay.
I'm pretty sure you can.
Okay.
So I think that's where you would do that.
But after that, does it have to access that like, you know, from a user space or from the kernel?
So from user space, then what you do is if you have a pool, if you have a particular pool that's a CMA block that's associated with that type of memory. Usually this is done for different banks of memory, but for secure memory it's probably the same thing. You have a block ID that gets associated with that block, that CMA block. And then from user space you can say allocate physical memory of this size from this block, ID 5, where ID 5 is mapped to your secure memory. I think that would
And
work.
it would work. It doesn't have to actually access that memory to allocate memory, right? That's all I'm trying to
I guess
say.
the question
Allocate
is,
that memory to?
is the housekeeping
No.
of the allocation kept in the buffer space, or is it separate?
Separate.
Okay.
Let me think about that. Wait, I believe it's separate.
Because if the CPU actually accessed
I think
buffer
it's,
it's
yeah,
talking
yeah,
about,
right,
it's
it
gonna
wouldn't work.
fault, right?
I'm trying to see the code in my head. So there's kmalloc. I think it's separate. I think the buffer descriptors are in kmalloc. I think it's separate. I have to look at the code. Yeah, we haven't looked at the security. Good question. So the memory allocation is done, buffer tracking, mapping to user space. And right now we're working on trying to get it to work for allocating huge buffers of greater than 2 gigabytes. One of the issues was that CMA, the DMA Alic coherent, to try to get a very big buffer, it uses up kernel virtual space, and you can run out of that. So there's some lower level functions to just allocate the physical CMA memory without doing the virtual mapping, kernel virtual space allocated. And then you can deal with things later, but the problem is that's not exported to the CMEM. That symbol's not exported to the CMEM library right now. It's insmodded, and so if it's built in, it works. There's some workarounds we got to do to make that work, but it's possible to large blocks of memory. We just have to figure a nice way to do this. And I'm not sure if that's an issue with some of the other memory allocators out there, like Ion or. So there's this other library that GI has, and it's used by the transport layer Ethernet driver I mentioned before that lives in user space. And there again, they just need the ability to allocate some physically contiguous memory. So they created another little module that does a little part of what CMEM does, which is allocate, in their case, allocating a 16 megabyte CMA buffer and then mapping it into user space. Now again, this is a user space Ethernet transport driver, so it needs to program DMA needs to know physical addresses. They're only getting one virtual physical translation because up at user space, they cut up the memory and they can use offsets to get the physical addresses, which are programmed to the DMA directly. So yet another solution that does something kind of similar to CMEM. In this case, they need to be able to also handle the when they're flushing cache, rather than let the kernel do it through, like say via dma-buf does it through callbacks, typically at certain times, attaching. But in this case, there's no dma-buf. This is just grabbing a buffer. If it's cache, it's determining when it's going to flush the cache before it does the DMA and doing the write backs at the right time, all from user space. So that's another solution. So when you look at these kind of things, you look at the code, it's like, well, doesn't everyone kind of need that? Isn't there something else there that is out there that we could use? So so there's some of the other things that exist. Ion, we talked about internally DRM, Gem Prime, and then recently CNAlic, dma-buf, which are all things that are kind of related to what we're doing in just different ways. So looking at Ion, so Ion is used in OMAP 4 devices. We also use CMEM. So some of the pros and cons, and I have some question marks, so I'm not really up on Ion and DRM, but my understanding is it provides separate heaps. I think there's a patch for CME pools in Ion. There's a way, or there used to be a way, I don't know if there still is, to plug in allocators or make a custom allocator as a user space API. From user space, you can do cache operations. Well, at least there was a sync ioctl. I don't know. I think that's been deprecated. DMA support, dma-buf support was added, so that's a nice thing. The one requirement for one of the use cases for the Ethernet transport driver was to get physical addresses from user space, and I'm not sure, maybe someone could correct me if Ion allows you to do that, but I don't think you can do that with Ion. And though it's in staging, it's not evident that that's going to mainline, but there's been a lot of discussion and work. John?
No. The interface is awful, so I mean, it's one of those, what it does is useful, but it's each platform that implements Ion, their APIs are fundamentally manufactured because they have hard code IDs for EIDs, and some of those overlap between implementations. Because you can't extend new allocators. Everybody's done that for their own platform. There's no centralized enumeration.
Yeah, it seems that, so some of the things that Ion has, it looks pretty attractive. So the ability to, well, that you have some kind of central area where you can have different allocators. And I understand that, well, so one thought is if you have one allocator, or one type of allocator that is very generic, and if that even, such a thing as an allocator that's very generic. But I'm thinking the use cases that we have are not so unique to TISOC. And that if you had that kind of a central allocator, and that's kind of why I was interested in seeing Alic, because it's called central allocator, but it's not really. I mean, it's a framework for central. Well, it's a framework. But it's not implementing all the allocators. So somebody has to implement the allocators. But the nice thing is there's one place to go. So you don't have the CMEM API you don't have another driver that you've got to build into your kernel. If you want to pick a different allocator, it seems like it would be nice. The thing I did like about Ion is the heap ID. So you could say up front that you wanted to. I'm probably getting ahead of myself, but that you want to get something from this a CMA pool, and because in the case of CMEM in the use cases, we typically don't have the constraint, the need for the delayed allocation. Well, in one of the use cases, for example, like a lot of embedded use cases, somebody's got a driver, they've got some data coming in, or they have data coming in from someplace, but it's not dma-buf-able, dma-buf ready. And they need to just allocate a buffer and put some data into it and send it off to the DSP. So in that case, you just want to be able to say, yes, I want to allocate a buffer, and it's going to be this. This is the buffer it's going to be. And it's true that when it sends it to the DSP, it's going to be through a dma-buf. It's going to a Vertio device driver, which imports it. But at that point, it's not sharing with a lot of other stuff. And so you could say up front, I'm going to allocate it, and it's going to be of this type of heap. So that seems to have gone away when we moved to Synalic.
Yeah, so you go ahead.
I know, but I'm jumping ahead a bit. But so some of the cons, Ion, yeah, it's probably not going to go forward.
So was getting the physical addresses, is that okay up in mainline if you are able to get the physical addresses of buffers?
Well, yes and no, I guess. I mean, there's a framework, UIO framework for writing user space device drivers, and I believe in that framework there's a way to get physical addresses. So I don't know how that plays with everything else, but generally you don't want to have physical addresses or map even map to those addresses and write to physical memory. I mean, get the physical address. But UIO allows you to write these DMA registers, if you have a DMA device, to write DMA registers and all this stuff. And I'm not sure how that plays with security. I really don't. It's usually secure. The issue is security and exposing those addresses. For a lot of the use cases we have with CMEM, I think except for that user space transport driver, getting a dma-buf is fine. So in that use case I was talking about, where the user space application wants to fill a buffer, get a buffer, fill it, and send it off to the DSP through RP message Vertio device driver. Well, RP message device driver, we'd add dma-buf import to it. CMEM, we can make it a dma-buf exporter, and you can mmap from that. Once you have your dma-buf file descriptor, we can mmap, so the user space can get a virtual address and write to the buffer, and then send it to the RP message device driver. Everything's happy, pretty much. So, I mean, that's one of the next steps we're probably going to do with CMEM, is add dma-buf support so it can export a dma-buf. We'll be talking about that. So that's Ion. We talked a bit about internally gem prime. There's some buffer management there. I can't claim to really understand it all, but just based on what I understand is it's very tied into the graphics world. Graphics buffers, video buffers, handles a lot more stuff than we care about. So it's managing display buffers, GPU buffers, handles command execution, write combining, domain tracking, and other stuff that I don't know if we really care about so much. There's no real user interface for gem memory management, as far as I understand, in user space, so you have to write a device driver again and have your own API and export something to create these gem buffers. There's no concept of pools of fixed buffers, which is something we already have in CMEM, so you have to implement that on top, as far as I understand. So, you know, this is something that there is memory management there, but it doesn't look simple enough for what we need. It's more complex than what we need. So the work that's recently being done with Alic, dma-buf, and there was an RFC put out by Sumit in Linaro, UMM team, and well, actually, John Stoltz did a lot of work, and other people. The idea there, in a nutshell, was to solve some issues with ION and basically involving constraints, sharing between devices. So sharing a buffer between devices. At the time you allocate the buffer, you want to, if you have a buffer being shared between multiple devices, these devices might have different constraints on how they allocate the memory. And so when you allocate the buffer, there's operations like dma-buf attach, dma-buf map attachment, during which times you can give energy to the exporter so that he can check constraints mask to ensure that he's allocating the buffer of the right type of memory that satisfies all the devices for sharing the buffer. So Alic was proposed as a separate solution, sort of a new device through which you can set your constraints, and there would be actually some allocation helpers that you can implement through Alic, do the allocation. And an RFC was put out, and there's been some discussion about changing it and merging some stuff back into dma-buf, making some dma-buf allocation helpers instead of separate Alic helpers. So some of the work that I did was to actually, I'll show you some code where I'm trying to use Alic, but that's based on the RFC, which is probably going to change. So, but I can go through it anyway, see how it works. But one of the pros with the Alic approach is that, well, it uses dma-buf, so that's great. One thing that it seems to do, which is kind of like what I thought would be nice, but I think it's actually is not in the requirements, is that it allows a unification of allocators under a central framework device. And I don't think that was really the goal, but maybe.
Yeah, it's one of those things where different people have different desires for that. I feel like a lot of folks want to focus on getting rid of dma-buf helpers so that
That's the key.
you know, basically interfaces that are using the DRM, the gen allocators can get the same benefit.
Mm-hmm.
But there is a desire as well to have a centralized allocator that kind of unifies that this is where people are pulling memory from. But
Yeah, and
I'm
that's.
not sure if that's going to go completely.
Okay.
And at some point, I think it will to some extent, because people are saying right now that, well, you'd use your gem allocator and it would use this in the back end and this will do what you need. But at the same time, I feel like at some point people will start writing special gem allocators that they use as a central allocator if we don't just provide it. So we'll see.
Yeah, so that was one of the things that I saw would be an attractive feature. Is having just being able to go open dev, Alic, ioctl, Alic, your params, and you get your buffer, and then you get your DMA-buf, and then you pass that on to other people, other drivers that import it and do all the operations needed to do everything the DMA-buf way, which is very nice. Yeah, it allows for the memory constraint sharing, which we probably don't have so much of a need for, but it's nice that it's there. And I believe there was a way to get physical addresses to send out. At least talking to Sumit, he was talking about adding it, but maybe he was just trying to be nice.
That's not ringing a bell for me, but.
Okay, all right, well, that could go to a con. Yeah, selection of pool ID was not really the idea with Alic. The idea was that the selection of the memory allocator would happen in a delayed fashion. I don't know if it can be either or it has to be delayed.
So basically, I think the idea is that we don't want user space specifying the memory.
Yeah.
We want the set of devices creating the constraint for the memory.
Right.
And so that basically user space says, I want to use this sets of devices, and then the proper memory gets allocated. That way, user space doesn't need system-specific knowledge of what kind of memory it may be using. It just creates a better abstraction so that user space isn't so tied to the particular hardware.
Okay. Yeah. So that's so the example that I put together kind of shows what that would look like if you don't have that knowledge. In user space.
The one gotcha for as far as a method for being able to do this that one of the Android guys came up with, because there are times where the delayed model is not, I guess, you can't really do it because you need to use the memory before you necessarily attached it to everything that you
That's
might
the
not
use
know what
case.
you're going to attach it to.
That's our use case.
And in that case, a pretty good idea was that you can create a system-specific driver that creates basically a dummy device that has the constraints that you want. And then that way you're able to have your user space attached to that device first. And then as soon as it uses it, the constraints just happen. And so because it's the only, you've customized the driver for the constraints that you want. And that way you're able to keep your user space agnostic outside of just saying, oh, I want this dummy device to be able to live.
So the dummy device comes up first before the user space app even talks to it?
Well, so the user space app would attach it at first, the dummy device, and immediately map the dma-buf, and that way the allocation then happens, and it happens with the constraints that dummy device provides. So that would kind of get around this concern, but it's a little bit of a
hack.
Well, it's not. It's the hard part is trying to keep a clean user base interface, and then still get that requirement.
So yeah, just talking to that, this is kind of an example of how we would use that in Alic, which is using delayed allocation in a use case where here this program is trying to it's going to allocate a buffer. So this is we're assuming that we have CNAlic. We have a CMEM allocator under CNAlic plugged in. And at boot time, we've made the call to CNAlic device add allocator. We've added our CMA allocator function. We've registered that with CNAlic. And we want to allocate the dma-buf for CMEM buffer. So we open the CNAlic device. We set some allocation flags. Now, one of these flags, I know I want a CMA, so I'm adding a pool ID, and I know that's probably a no-no. But I want to be able to say I'm getting it from the CMA pool, so it gets this guy. Payload, do the octal to get do the create, which that exports the dma-buf, but it's not yet allocated the actual buffer, it's just the dma-buf. So we get our file descriptor, which is the dma-buf file descriptor. And then we want to really allocate the buffer. So here what I'm doing is prodding, it's not really a dummy device, but I'm prodding the importer at this point to say, giving a special command saying, the importer in this case is our RP message socket device driver, which talks to the DSP through Verdio, and I'm prodding it and saying, okay, now do the allocation. And so this is going to do the dma-buf map attachment stuff. So that delayed allocation is now going to happen. And then payload is the pointer to the CMA buffer. It's doing a map on the buffer file descriptor. So now I have a pointer to that buffer. And then I'm going to just start filling the buffer, reading from a file here, or standard data, whatever. Reading data into the buffer and then sending it through the RP message socket device to the DSP. I'm just sending buffers down to the DSP. And then when I'm done, close the CLI file descriptor. But what I'd like to do is not have to do a second call to this RP message socket driver to say allocate from the to the importer, to tell the importer to allocate. So sure, I could avoid CNALIC completely and just have CMEM be an exporter of a dma-buf and just avoid the CNALIC framework completely and just take my dma-buf, map it right to it, and then just send that to the RP message driver. But there again, we have this CMEM device that has an API that's sitting out there, and you have to load it, you have to build into your kernel, or you have to insmod it, and we're back to square one. So if ION's going away, and CNALIC is going to be replacing ION, what about some of the features that ION has that might be useful that aren't being replaced, like the ability to specify a pool ID up front without writing a dummy driver, or something like that?
To some extent, it's that aspect of how much
Interest?
Well, I mean, it's that aspect of trying to get something upstream. We have to have an interface that kind of will pass muster. That isn't, you don't need to have user space know exactly everything about that specific hardware to be able to do the right thing.
Well, here I'm not really saying much about the hardware. I'm just saying make it a CMA type thing.
Yeah.
Now, there's something hidden. There's some hidden stuff here. For example, I know my CMA pool is coming from this allocator, which can handle fixed. It's got a lot of capability. It can do heaps. It can do fixed size buffers. So I've got that capability under this thing. Let's not call it CMA pool. Let's call it a generic allocator, and anyone can use it. If we didn't need the delayed allocation, we could do one or the other. Maybe a flag. I don't know. So it's like we're very close. It's like I want to use this, but ION seems to be pretty good, but it's going away, and we're close.
I mean, it's.
So this is just raising the. So it's kind of raising the issues for the some of the requirements and
So this is the allocation flow, but things like being able to allocate very large blocks, that almost, if you got 8 gig on a platform and you want to reserve 4 gig of it for coprocessors, that almost seems like something you're gonna want to know at boot time, because doing it later is going to be very problematic.
yeah, I think you do know it. Well, if you do that CMA reserve, that's done very early.
Okay. But I
mean, that's the reserve.
CMA has a limit of like 256K or something.
So yeah, there were some issues with actually, one of my colleagues is working on CMEM with CMA, and he's had to tweak the kernel a bit to get it to get bigger sizes.
Is that just an artificial constraint somebody put in, or is there an architectural reason?
Actually, I don't think there's a, the problem was, I think it was printing the size, the print function had to be changed. But I think it was allocating a larger size. I don't think there's really an issue with CMA with size so much. It was the issue we had really was the virtual memory that was consumed when doing the dma-Alic coherent, and having to work around that by using a private function from the CMA module that wasn't exported to the CMEM module. So I think one of the questions was if we did that, and Linux didn't know about the fact that we had allocated this huge CMA block, because it it would know that we allocated the CMA block, but I guess we just have to understand, can we use CMA the way that we were doing by using this lower level function that wasn't doing the kernel virtual mapping, and still allow Linux to migrate pages the way it wants to if we're using some lower level private functions. So there's still some issues
I thought there was an architectural limit that CMA could use high-net at all. It was only kernel virtual space that was a potential for CMA.
But the guy at my colleague has made a patch that's allocating 6 gigabyte buffers.
Okay.
So he's got around that. And I think it was really by just not calling dma-Alic coherent, but calling DMA. There's some CMA function, lower level CMA function that's not exported. So anyways, so CMEM seems sufficiently generic, but it doesn't require the delayed allocation and constraint sharing features the CNALIC has. But it seems like it would be useful to plug CMEM type allocators, if they're generic enough, into some kind of a centralized dma-buf allocation framework. And maybe with these dma-buf allocation helpers, maybe that's something that could be the path to do something like this. I think I read somewhere that like some of the ion heaps, that they could become allocators that would go under CNALIC.
So basically, the types of memory that ion drives, basically those are types of memory satisfies different types of constraints. And so basically we're trying to just switch it from being an explicit memory request to a constraint solved request. And so it's one of those things where if you do have a specific thing that you want to force, you can hopefully have these dummy devices that would force that constraint. But it's just a matter of trying to find a way to keep that, because we may, I guess we don't want to standardize those types, because there's just, every system has a different set of types. And so it's one of those things we're trying to find. There are some common ones, but when you look at like the different implementations of ion are vastly different. I mean, between SoCs, there's just there's almost no similarity.
Like the CMA allocators are different themselves.
Pardon?
The CMA pool allocators are different
Well,
themselves.
the different ion heap allocators, yes. And it's just because they've all got their own.
They'll end up fragmenting anyway. For the
So
system.
we're just trying to
The
keep
idea.
that amount of awareness out of user space.
Well, and having a device driver for the DSP doesn't sound like much of a burden. And some of these other devices, we have device tree annotations for the UIO nodes, and this could be a property of
Well, yeah,
that, so it might not be a lot of code to write, it's just, you know, some attributes that go into the right driver and create these device nodes that then can be used.
So, yeah, there's the DSP, and then, like I mentioned before, earlier, that this guy, doing something on Intel Atom, he doesn't have a DSP. He just wants to allocate, some memory to this endoscopic application that he's going to send to OpenGL somehow. Maybe up on Alaska or what, but he just wants to grab a chunk of CMEM memory. And, he was asking, he's got CMEM. He grabbed CMEM from us and he's porting it to Intel. And, so it seems, you know, there's some generic capability there, and
Yeah, I guess in that case, he's not gonna have the device straight. And there's not gonna be any ACPI table that tells him, by the way, I have this endoscope hooked up. So, I mean, that was kind of my reaction to what you were saying initially was, well, sometimes you know, it's the application knows more about the system than the kernel does, right? And in this case, right, that's, you know, it's only this user's application that understands that he's got this endoscope, right? The kernel doesn't really know that.
That always gets into another situation in the long term. I mean, it's one of those things where, you know, how do you then maintain that application that becomes totally unportable at a certain point, right? You have to have some sort of abstraction.
Well, yeah, if he wants to get the endoscope application in Red Hat, it needs to be
And I think
portable.
CMA is a little bit simpler case to some extent because it's an easier constraint to describe than what we see in a lot of the SOCs. And so maybe it would be something that would be more easily flagged when you had, for example.
the constraint sharing idea is elegant. I really like it. It's just how to make it work.
Yeah.
So the code looks elegant.
But
At the
I'm excited
top
to
level.
see the example of the insight, because it's one of those things we're getting some feedback on it has been slow, I guess. So it's one of those things where we're seeing real interest in how I'm excited to see at least, and having the issues brought up. So appreciate that.
Okay, any other questions or any comments?
Any other vendors?
Yeah, other vendors who need that kind of capability that CMEM has.
Definitely, same problems.
Have you looked at what's your system?
Oh, used to be LSI, then became a VAG, and then we're bought by Intel.
Intel?
So it's a Axia networking SoCs,
Ah, okay.
like the Keystones.
Magnus, what are you using today?
I'm actually using Intel as well. I change every single Linaro connect.
No. I mean, in your LSI
Oh, just
ODP implementation.
a memory serve. Is in the
what?
device. Because we have like 32 gigs of memory and 31 gigs are not used by Linux.
Okay.
You know, we maybe use 1 gig and the rest is just for networking accelerators. So we have to carve it out in the memory server. And what we did previously, I mean, if you don't care about the virtualization, we just said, command line mem equals 1 gig and the rest Linux didn't know anything about. But if you introduce virtualization, you actually have, Linux has to know something about the rest of the memory. And that's where all the problems come from. And then you actually have to carve it out from Linux. It knows how to set up all these stage 2 translation tables and stuff. So yeah, I'm all for a solution to this. It will be great. And we have exactly the same problems as you.
I know Bob Clark is here. I don't think he's in the room. He would be someone else to speak to. He definitely is kind of a gatekeeper here on the side.
Okay.
Making sure he's understanding the levels as well.
Okay, he's probably pretty aware about this code being a TIR at one time. He's probably combed over it. Okay. All right, well, thanks. Thanks a lot.